Hi and welcome to a lesson of multivariable calculus. So in the previous lesson, we talked about equation of lines, equation of planes, and then we talk about traces of surfaces on different planes. And we also learned how to draw the surface using the traces. Now in this lecture, we are going to learn quadric surfaces, right? So the word quadric uh, represents a surface, just like if we talk about a quadratic equation, as we all are familiar with a quadratic equation. It's quadratic because its power is 2. Therefore, we call it a quadratic equation. So the quadratic surface, equation of the quadratic surface is in general form is given by ax square bx square plus cz square plus dxy plus fyz plus gx plus hy plus iz plus j equals 0, right? So it's just like if we remember general equation of a conic section. So in 2-dimension equation of conic section is given by ax squared plus by squared plus 2cxy plus dx plus fy plus e equals 0. So this is the general equation of a conic section in 2 dimensions. So we can say that this equation here may represent a 3-dimensional view of or 3-dimensional part of conic section, right? So in 3-dimension, in 2-dimension, we have a circle. So the equation of circle is given by x squared plus y squared equals to r squared. So just like this, in 3-dimension, if we add one more dimension, that is x squared plus y squared plus z squared equals to r squared, so it represents a sphere. All right, so it's a sphere in 3-dimension like this. Okay, and similarly, if we have equation of this form, that is x squared or a squared plus y squared or b squared equals to 1. So this is an ellipse in 2-dimension, but if we add one more dimension in this equation, let's see what happens. It's x squared or a squared plus y squared over b squared plus z squared over c squared equals to 1. Now this is the extended version of this ellipse in 3 dimensions. So it will be an ellipsoid like this. So it will be an ellipsoid like this, right? So we can think of an egg. It's an egg-like surface, right? So it's ellipsoid, right? So these surfaces are called quadric surfaces. So now we will see how to draw these quadric surfaces and their by using their traces, right? So let's move to an example. Now see here, it's equation of ellipsoid as just we talked in this lesson, just right. Now x squared over a squared plus y squared over b squared plus z squared over c squared equals to 1. Right now, if we want to draw the traces of this equation, that is trace in xy, yz, and xz plane, what we need to do is we already learned in the previous lesson, right? So now let's see how to do it, right? Now, if we have this equation, one thing we can do here is that if I exclude this z in this equation, I will be only left with x squared over a squared plus y squared over b squared equals to 1. Now this is equation of ellipse in xy plane. So if I am three-dimensional Cartesian coordinate system, so I can draw in this in this way. So it's x, it's y, it's z. So this is ellipse and xy plane. So my xy plane looks like this. For instance, looks like this. So it's like this. So it will be an ellipse on this plane, so I can draw it like this. Right, so it's an ellipse on xy plane. And again, if I want to draw its trace on yz plane, this is the trace on xy plane. Now if I want to draw it on yz plane, what I need to do is I need to exclude this variable x from this equation. Then I will left with y squared over b squared plus z squared over c squared equals to 1, which again is equation of ellipse, but this is in yz plane, right? Having y and z coordinates only. So this may look like this if this is the coordinate system x, y, z, and this will be the yz plane. This will be the yz plane. Now this ellipse will look like this on the yz plane, right? Similarly, if I want to draw its xz trace, I need to exclude this y variable, this part here. So I will left with x squared over a squared plus z squared over c squared equals to 1. Then I will get an ellipse on the zx plane. So it will be xz trace like this, right? So this is xz plane, this one here, and the ellipse look like this. Okay, so now combining these three traces and the Cartesian coordinate system, we can draw the surface, that is, we already called it as ellipsoid. So this is our coordinate system. Now this here we have the zy trace here, and then we have x and z trace, so it looks like this. It will be like this, and the trace on the xy plane, it will be in this form. Now we can see that this whole surface is nothing but just an ellipsoid. So this is an ellipsoid, right? This is an ellipsoid. So this is the way to draw a surface by using idea of the traces, right? Now let's see even more example. Here we have hyperboloid of one sheet. So the equation is given as x squared over a squared plus y squared over b squared minus z squared over c squared equals to 1. Now its xy trace will be excluding this z. The xy trace will be an ellipse because the equation we are left after removing this z variable is the equation of ellipse, right? So the xy trace is an ellipse. So it will be an ellipse in the xy plane like this. Okay, so this is the ellipse in xy plane. And again, if we now want to find the yz trace, so the equation will be like this. So now this is equation of hyperbola, right? So the YZ trace is an hyperbola. So the YZ trace will be an hyperbola. So let's draw YZ plane first. So it will be, this is the YZ plane, this one, and we have a hyperbola on this plane. So it will be like this one, like this. So it will look like this, right? On the YZ plane. And again, if we want to find the xz trace, we need to remove this y variable. So again, we will get equation of hyperbola. So the trace on xz plane is again a hyperbola. Now, what we need to do is we need to join all these traces to find the surface. Now, see here, the xy trace is an ellipse, and the yz trace is a hyperbola like this, and the xz trace is again a hyperbola. So it's again a hyperbola. Now combining these three, we will get this surface. So it's called hyperboloid of one sheet. So this part here, this one is obviously in, you can see that this is the YZ trace, and similarly here we will have XZ trace. If we draw the plane, that is XZ plane. So the XZ plane will look like this. It will look like this. And now the hyperbola here, these hyperbolas will be like this, right? Like this. So these parts here will also be hyperbolic, and you can see the cross section since it's elliptical in the xy plane. So we can see that this is elliptical cross section that is in the xy plane, right? So it's all elliptical. So this is called hyperboloid of one sheet, since it contains only one sheet, right? So it's a hyperboloid of one sheet. Okay, now this one here, this is called hyperboloid of two sheets. So the equation of this surface is given by this formula. The difference is that here we have x negative, y negative, and z positive. But in the previous case, we have x positive, y positive, and only z as negative, right? So this was the previous case, hyperboloid of one sheet, and hyperboloid of two sheet is both x and y are negative and z is positive. So the trace are traces of these xz trace will be a hyperbola. Again, the yz trace is also a hyperbola, but this xy trace, that is negative x squared minus y squared will be equals to 1. So if we combine this and shift this negative side on the right hand side, so it look like equation of an ellipse, but because of this negative one, we can see that the roots of this will be uh, above the origin, right? So we can see this surface. Now see here, this is the xz trace, it's a hyperbola as we already talked, and this is the yz trace, right? And now the if you combine these and for this x square this xy trace, we can see here that if we shift this negative sign by taking it common onto the right side. X squared over a squared plus y squared over b squared equals to -1. So this negative sign here suggests that uh, the circles that you can see here, these circles, basically these are ellipses, not circles. So these ellipses are above and below the origin, not on the origin, right? Because of this -1. So in this manner, we can draw this surface. Okay, now let's see some more surfaces. So it's a cone, equation of cone. It is somewhat similar to the equation of hyperboloid of one sheet, but here we have 0 on the right side in this case for the cone. But in the case of hyperboloid of one sheet, we saw that it was x squared over a squared plus y squared over b squared minus z squared over c squared equals to 1 for hyperboloid of one sheet, right? But for the cone, the right side is 0. It's just the difference is that. Now find the traces. If we make this 0, so we'll get x squared over a squared plus y squared over b squared equals 0. This means that x squared over a squared equals to -y squared over b squared. So now this represents not this trace. Let's first see the xz trace. So for xz trace, we will remove this, so it will be x squared over a squared equals to z squared over c squared. So it will be x equals to plus minus z az over c. So this represents a pair of a straight line. So these will be straight lines like this on xz plane, because it's plus az over c and minus az over c. So the slope, if we compare y equals to plus minus mx, so we can see that the slope is positive and negative. So for the negative slope, the line will look like this, and the positive slope the line looks like this, right? So the xz trace is a pair of straight line of this kind. Similarly, the yz trace will also be pair of a straight lines. Okay, and now this equation here, that is x squared over a squared plus y squared over b squared equals to 0. We can shift this to the right side like this. Again, we have x squared equals to negative a squared y squared over b squared. So we'll get x equals to plus minus a y b iota because of this negative sign if we take a root on the both sides. So now this this equation here, this is imaginary, right? So this is imaginary. So what this equation represent is, this represents an imaginary line, right? Because we have the imaginary number here, that is x equals plus minus a over b y iota, right? So because of this imaginary number, we can say that this is an imaginary line, but we are drawing these surfaces on the real axis, therefore we cannot represent this thing here. So therefore now if we can do one thing, that is we keep x squared over a squared plus y squared over b squared on the left side and move this z squared over c squared. And if we uh, take this as a constant, let's say it's a constant, for instance, if we fix z, and we can say that, let's say it's a constant. So now this represents equation of ellipse. So we can see that the xy trace will be ellipsis, right? So it will be elliptical like this. And here also we can see that like this. And here also we will have ellipses like this, right? So this is the surface represented by this equation that is called the equation of cone. And for paraboloid, now the next case is the paraboloid. Here is the equation. So in two dimension, the equation of parabola is like y squared equals to 4ax or x squared equals to 4ay. So similarly, in the three dimension, it may look like x squared over a squared plus y squared over b squared equals to cz. Now we can see that this thing here, it resembles the left side of an ellipse, right? And we can now see how its trace works, right? So it's x squared over a squared plus y squared over b squared equals to cz. Now, if we take this as a constant, for instance, if we make it k, then this is the ellipse, right, on xy plane. So we will get ellipses. So first of all, if we take z as 0, so at origin, it will be a point simply. So if we can see here, so at origin, there is a single point. Now, as we increase this z, let's say this cz is equals to 4, then we will get an ellipse at z equals to 4, right? So if this is x squared over a squared plus y squared plus b squared equals to 4, let's say, now we will get an ellipse on the centered on the z-axis. So we will get ellipses like this. So it will be a family of we will get family of ellipses, right? In with like this. Now, if we join these all ellipses, we will get a paraboloid like this, right? So this is a paraboloid. So this equation is equation of elliptic paraboloid. So whose cross section is elliptical. That's why it's called elliptic paraboloid, right? And its outer surface, that is its front image or its back image or side image, it will look like a parabola. And the cross section is elliptical. That's why this is called an elliptic paraboloid, right? Similarly, there are more examples, and these surfaces are the more used. These are most used surfaces in mathematics. You can see these surfaces. Uh, we learned these in elementary classes. Not these surfaces, but they are two-dimensional uh, traces. There is ellipse and parabola and hyperbola, cones and ellipsoid, circles. But here we can see that if we extend those in three dimension, we will get for ellipse we have ellipsoid, and then for hyperbola we have hyperboloid of one sheet, hyperboloid of two sheets, and for the cone in two dimension, this extended part is again a cone in three dimension like this. And then for parabola we have a paraboloid, right? And and one more surface, this is called hyperbolic paraboloid. So this section concludes here. In the next class we will start discussing limits and continuity and partial derivatives. So thanks for watching the lesson.